Welcome to Pavinars, webinars for the pavement community. My name is Andrew Braham, and today we'll be talking about the evaluation and compaction of laboratory-produced recycled asphalt pavement in cold-in-place recycling. And you can see here an image of how we attempted to create RAP, or reclaimed asphalt pavement, in the lab from virgin materials. And this is a picture of what we called 75P25C, and I'll talk about that a little later in the presentation. This work is based on Erica Bowie's, previously Erica Yeung's, master's thesis research, and it has the same title, Evaluation and Compaction of Laboratory-Produced Recycled Asphalt Pavement in Cold-in-Place Recycling. Erica received her Bachelor's of Science from the University of Arkansas in Accounting in 2009 and her Bachelor's of Science in Civil Engineering, also from the University of Arkansas, in 2015. Finally, she also obtained her Master's of Science in Civil Engineering in 2017. And you can see her LinkedIn profile here, and it is also shown below. Let's start out talking about the Superpave Gyratory Compactor, or SGC. The SGC was introduced in 1993, and it was a part of the Strategic Highway Research Program, or SHARP. And you can see on the right-hand side two pictures. The picture on top is a Pine SG2 compactor, and then the picture on the left is a Pine SG1 compactor. My personal favorite, that is the original Pine compactor, and that is the compactor that I used for years at both the University of Wisconsin and the University of Illinois, but that's just a little personal bias of mine. Either way, regardless of the type or the brand of compactor that you have, at the end of the day, you're applying 600 kilopascals of pressure to a sample in a mold. It's tilted at 1.16 degrees of an internal angle, and then the sample is rotated, and each rotation is called a gyration. And you produce either 100 millimeter or 150 millimeter diameter sample, so approximately 4 or 6 inch diameter sample. And you can see a typical compacted sample. So again, you take the sample loose, you put it in the mold tilts at a 1.16 degree internal angle. You apply 600 kilopascals and you rotate that mold, and each rotation is called a gyration. And the benefit is these samples are made during the mix design and for performance testing. So we're always making these samples in the lab. So the question is, what kind of data is collected while we're making these samples in the gyratory compactor? Well, there are two pieces of data that are collected in all compactors, and that is the height, which is generally millimeters, and what I just described, the number of gyrations. So you have the volume of the sample because you know the diameter of the mold and you know the height you're at. You have the mass of the sample because you weighed it either just before putting it in or just as you're taking it out of the compactor. So you can calculate the density. And you can see here, you can create a graph of the density versus the number of gyrations. So again, you put your sample in the mold, it tilts at 1.16 degrees for an internal angle. You apply 600 kilonewtons or kilopascals, and then that mold gyrates, it rotates, and each rotation is called a number of gyration. Now, if you're interested in some background on this, I encourage you to look at the work that Dr. Bahia and his research group performed at the University of Wisconsin-Madison, because they really pioneered using this data in order to get more information out of mixtures. And they started the development of compaction metrics, and it's really taken off since then. And one of the reasons is, again, you can collect this data on every sample you compact in the gyratory compactor. And the data is already being collected, so the question is, how can we further leverage the data that's already being collected in order to better understand our mixes? Now, this is an unbiased plug for a very nice paper, also an unbiased statement, that myself and three gentlemen from Ingevity wrote about 6 years ago now. but it's called Characterizing Compactability of High Wrap and Warm Mix Asphalt Mixtures in the Superpave Gyratory Compactor. And the reason that I recommend this paper is that it does really go through all of the different SGC compaction metrics. So if you're interested in this topic, this is a place to start because it goes through almost, I believe, all of them that we were able to find, and it'll give you a really nice background on it from an asphalt concrete perspective. Here's just an example of some. So again, you can see your density and your number of gyrations. And the way that you play with these compaction metrics is you can either go off of the number of gyrations on the x-axis or the density that you're targeting on the y-axis. So you can see here N8, N equals 8 is the beginning of the CDI, the compaction densification index, and then the density, the 92% density, or you have 8% air voids. That is the beginning of the traffic densification index, which goes all the way to 98% density. So that's just the CDI and the TDI. And then other ones, the WEI is where you go from N equals 0, so the beginning of it, to 92% density. And WEI is the workability energy index. And then the CEI, the compactability energy index, is from 92 to 96% density. So just different metrics to play around with these curves and try and extract a little more information. Now these were all developed because asphalt concrete has 4% design air voids, but cold in place recycling, or CIR, has 10 to 12% design air voids. So how do we start synthesizing those concepts? Well, before we go there, let's just go over a brief recap of cold in place recycling. Here's an example of a CIR train moving away from the photographer, and closest to us in the foreground on the far left is the asphalt paver. Then you have a pug mill mixer, a screener and crusher, a milling machine, and a binding agent truck. So let's go through that in order as the road sees it. So the first thing you do is you add any sort of binder agents. So that can be water, it can be Portland cement, it can be lime, it can be asphalt emulsion, it can be asphalt foam. You mill the existing pavement, and you may or may not have a screener and crusher. It depends on exactly what you're going for. But regardless, you do mill the pavement, and then you use a pug mill mixer to mix the existing pavement with the binding agents. Now, some trains also just have a milling machine, and that mixing occurs in the milling head. But regardless, you take your existing road, you mill it, and you mix it with a binding agent. And you may or may not have a screener and crusher and a pug mill mixer. But then you put that mix into a traditional asphalt paver, and you place a new road. So what sort of metrics did Erica develop for cold in place recycling? The first one is the GCI, the Gyratory Compactability Index. And you can see here she used the height versus the number of gyrations. So she used the height where n equals 20 and the height where n equals 10. And she took the height of n equals 20 and divided by the height of n equals 10. And she was able to obtain the GCI for CIR. The workability energy index and the compactability energy index were similar to asphalt concrete, but the WEI-CIR went from n equals 0 to 76% density, and the CEI-CIR went from 76% density to 88% density, the areas under the curve. And then she also collected the compaction densification index, which was from n equals 8 to 76% density. In addition to these four, she collected the N76, which is the number of gyrations required to reach 76% density. She did look at the locking point, and this is the second gyration of two consecutive gyrations to have the same height. So essentially when the aggregates lock together, that's kind of the point of the locking point. But after analyzing the data, she did not move forward with this because it was very poor consistency. And then also from these five that are shown here, that we're moving forward, the CEI was not used since the mixed design only reached 30 gyrations. And all this data was collected off CIR compacted samples through the mixed design procedure, so we only went up to 30 gyrations. Therefore, we did not use the CEI-CIR. Now let's take a little bit of look at materials. So as I mentioned, we did use lab-created wrap samples or reclaimed asphalt pavement. Overall, we used 3 types, 1 from the field and 2 from the lab. So the field wrap was a limestone-based wrap from a local quarry. Then P is what we call pre-coated. That's where we took virgin limestone rock, we coated it with 6% asphalt binder, and we crushed it. P is post-coated, which is where we crushed the limestone and then we coated it with 6% asphalt binder. And what we did is we did a grayscale analysis on various combinations of these. So you can see the grayscale on the right, and I'd like to draw attention to the field wrap, which is the red lines with the circle. It is in the middle, it's that middle peak that peaks around 100 for the grayscale intensity. And I'd also like you to take a look at the lab 25 P over C and 75 C over P, which is basically 25% of the pre-coated aggregate and 75% of the post-coated aggregate. And what we were trying to do is we were trying to mimic what happens in the field, where you have some aggregate that is coated and crushed, but then other aggregate that isn't crushed, so it's in a way pre-coated. And we found, based on our experiments, that the lab 25P over C and 75C over P, it best matched the field wrap based on a grayscale analysis. So we decided to move forward with that wrap blend in the lab. So by taking virgin aggregate and either pre-coating it or post-coating it after or before crushing, we were able to try and create essentially wrap in the lab. And the examples here for pre-coating and post-coating were for limestone, but we did the same thing with syenite, which is another type of aggregate commonly found here in the state of Arkansas. So we had one field wrap, and that was a limestone-based wrap. And then we had 2 lab wraps, 1 limestone, 1 syenite, and we used the 25-75 ratio of pre and post coated. Now that we had determined the wrap types, we explored 2 types of asphalt emulsion. These were both produced in our laboratory on a Rashig recirculating benchtop mill. We ran 5 quality control tests. We ran the residue, the pH, the viscosity, and the sieve. And you can see the target of the residue was 61 to 65, and both the proprietary and the commodity emulsion easily fell within that range. We're looking for a pH of the soap solution to be greater than 2.2, and both of the emulsions fell into that range. And excuse me, that was the pH of the emulsion, not the soap solution. The viscosity, we're looking greater than 50 centipoise, and the proprietary was fine. The commodity was a little bit under that, but we felt it was acceptable within the range of the variation of the emulsions we made. And then the sieve, we wanted less than 0.1%, and they were both 0. So that passed too. So we're looking okay on those 4 quality control tests. And the 5th was a particle size analysis. And there is no current specification for particle size analysis. So all we were able to do was measure the particle size. Now, in general, you want to see particle size less than 10 microns, and you can see the proprietary emulsion did a pretty good job at this, but the commodity was a little larger. So that was something that we wanted to keep an eye on and keep in the back of our head as we moved forward. So what were the results using these newly developed compaction metrics, the newly developed lab-created wrap, and this asphalt emulsion? Well, for N76 and GCI-CIR, we assumed that all the metrics, these 2 and the other 2, so all 4 metrics, were pre-traffic conditions, so it was all just the construction of the CIR that was being investigated. And from our standpoint, you want lower N76, lower CDI-CIR, and lower WEI-CIR. And that is because you want lower efforts of compaction in pre-traffic condition. So in theory, that's what we were looking for. Now, we could not really determine a trend of a GCI-CIR. We didn't know if it was lower or higher, so we just wanted to collect that data and see what would happen. And then finally, the proprietary emulsion was designed for better compaction. So in theory, this proprietary emulsion should compact better. From these graphs, you can see N76 followed expectations. So in theory, we were expecting the proprietary emulsion to, um, N76 did not follow expectations. We were expecting the proprietary emulsion to have lower compaction numbers for the N76, but it had higher, and the GCI-CIR was mixed. There wasn't any sort of trend that we could see. However, the GCI-CIR did have the tightest standard deviation, which meant that it was able to distinguish between what we felt the variation was between the replicates. Now, what is interesting is the cyanite always fell between the limestone and the field wrap. And this was unexpected because the limestone and the field wrap, those aggregate types matched. So we expected to see similar trends between the limestone wrap created in the lab and the field wrap because they were both limestone based, but that wasn't the case. The cyanite always fell in between them. And you can see that continues here with the CDI-CIR and WEI-CIR. With these metrics, neither of the metrics were clear. They both had high standard deviations and mixed trends. So the N76 did not meet expectations. The CDI-CIR and the WEI-CIR provided unclear trends. And we think some of the potential causes could have included the fact that asphalt emulsion has 3 stages. There's a workability stage, a compactability stage, and a cohesion build stage. And the difference between these 3 stages are based on the asphalt emulsion breaking. So as the asphalt emulsion breaks, you transition from the workability stage to the compactability stage to the cohesion stage. And we feel that these 3 stages may have overlapped in the metrics, especially the workability and the compactability. And we feel that this is especially true because we felt that the lab wrap did not compact in the same way as the field wrap. We expected the 2 limestone wraps, the limestone lab wrap and the field wrap, which was based on limestone, to behave similarly, and we just didn't see this. But again, we do feel that this may have been limited because the metrics only captured during the mix design and they were limited to 30 gyrations. Perhaps if we went further in the compaction, we would have found some further information. So in conclusion, for the CIR compacted metrics, we found that the commodity emulsion had a larger range of particle size versus proprietary. We felt that the phases of workability, compactability, and cohesion gain of CIR is not well understood. We felt that the field wrap and the lab wrap, both limestone, showed inconsistent trends versus cyanite, and that means our lab protocol for creating wrap in the lab may not quite be as robust as it needs to be moving forward. So that is certainly something to look at. And we found that the GCI-CIR showed the clearest results of the 4 metrics that we examined. So like all research projects, I think some questions were created here at the end, but this is a strong first step in understanding CIR compaction, and hopefully we can continue to move forward to better understand it in the future. So if you're interested in learning more, here is the title of the full paper, the full citation, and then the DOI is listed in the comment or the summary section below if you would like to access the paper. So I hope you enjoyed it. Thank you for joining me today, and I hope you have a wonderful day.